Hello, welcome to the probability class. In the last two sessions, we discussed about random variables. There are two types we discussed, discrete and continuous. Probability mass function relates to the discrete type and probability density function relates to the continuous type. Today, we will discuss another important function relating to the random variables. That's known as cumulative distribution function or simply distribution function. Let me bring out the PPT so that I can start discussing those. Here it is. What's cumulative distribution function? First, let me define. Suppose capital X is a random variable. It may be discrete or may be continuous. We are defining for both types. Just assume that capital X is a random variable. Then cumulative distribution function, in short CDF of capital X, is defined as this thing. We are defining the function fx. How is fx defined? This way. In order to define a function, we must assign one value to each number x. That's what it is doing. For any number x, say for example, for x equal to 3, how is f3 defined? That is defined as probability of capital X less than or equal to 3. We know that so far the random variable x is known. This gives a unique value and that unique value is assigned to the number 3. That's how f3 is defined. Similarly, f of, f of minus 1 is defined as probability of x less than or equal to minus 1. Or f2 is same as probability of x less than or equal to 2. Using the random variable capital X, we are defining a new function, capital F, and that's called the cumulative distribution function of the random variable capital X. So what does this thing mean? Say f of minus 1, that means probability of capital X less than or equal to minus 1, and the meaning of that thing is probability that the random variable capital X will be less than or equal to minus 1. That's the meaning. This is a very useful concept in probability theory. Let's try to understand that. Now, as we know, there are two types of random variables, discrete and continuous. First, let's assume that we are considering a discrete random variable, capital X. Please understand that while defining the cumulative distribution function, we do not need to assume the random variable to be either discrete or continuous. The definition is generic, the general definition. However, if it is discrete, then we get a certain form for the distribution function. Let's examine that. Suppose x is a discrete random variable and it takes values x1, x2, xn, etc. It may be either finite number of values or infinitely many values. It doesn't matter. The concept is same. Let capital Fx denote the CDF or cumulative distribution function of x, and small fx denote the probability mass function. Here we are considering probability mass function because we are under this case, discrete case. In that case, capital Fx is given by this formula. Why is it so? Suppose x takes only these 5 values. This is the real line. Now, here is your point X, and you are trying to compute fx. X is here between x3 and x4. What is the definition of fx? It is same as probability of capital X less than or equal to x. Now, capital X can take values only these 5 discrete points. Now, which all values will satisfy this event, capital X less than or equal to x? Either x may be equal to 1 or x may be equal to x2 or x may be equal to x3. X less than or equal to x, this event can be thought of union of these 3 events. Here, because if capital X equal to x4, this left hand side event is no more satisfied. Whenever the right hand side is satisfied, that is capital X value is one of these 3, small x1, small x2, and small x3, then of course capital X is less than or equal to small x, and when the other way around happens, then also capital X must be equal to x1, small x2, or small x3, because it cannot be x4 or x5. Those are bigger than x. Now, taking probabilities on both sides, we get these will add up because they are mutually exclusive events. And this addition of 3 things, I can write it as summation over I such that xi is less than x, fx. Please understand why this thing holds. I will have to check which all xi's are satisfying xi less than x. x1 satisfies. So in this summation, I'll include fx1. x2 also satisfies this. So in this summation, I'll include fx2. And in this summation, I'll also include fx3. However, x4 is not less than x, so I will not put the term fx4. That's why this summation represents the same thing as we have got here. We have got here that probability of capital X less than or equal to small x is f of x1. See, what is this thing? Probability of capital X less than, capital X equal to x1. What is this thing? This is fx1. I don't have much space here. Let me write down this thing. Probability of x equal to x1, that is nothing but f of x1 by definition. We have these things, 3 things from definition. And when we replace those, then we get fx1 plus fx2 plus fx3, and that is same as this summation. That's why this thing holds. Here we have just taken a simple example where capital X takes only 5 values, but that is generally true even when capital X takes infinitely many values. Let's take an example of discrete case. We are tossing a coin 3 times and let X count the number of heads. The coin is fair, so probability of head and tail both are half in each trial. Fx is the cumulative distribution function of capital X. Which all values capital X can take? Only 0, 1, 2, and 3. Because we are tossing 3 times only, and capital X is the number of heads. we already know that F0, we did this thing while studying discrete random variables. F0 is equal to 1 by 8. F1 is equal to 3 by 8. F2 equal to, again, 3 by 8. And F3 equal to 1 upon 8. We know this thing from our earlier study. So these four things we know. This. Now let's find out the cumulative distribution function of capital X. So what it means is we need to compute fx for all possible values of small x, that is for any x belonging to R. There are infinitely many values in the set capital R, but we just need to find out the pattern. Then we can write down the functional form of capital F. So let's divide the real numbers line into several components. Say, let's take one part, namely when x is less than 0. Let's see what happens to the capital F value in that case. Suppose x is less than 0. In that case, what happens? We already know this is nothing but I such that xi is less than or equal to x. Just let me check once. Did I do that thing in the earlier thing? Yeah. See here. So we are considering this case. We are considering this case. In that case, now which are the xi values here? X1, 0. These are the xi values. Now, among these xi values, in other words, the possible values of capital X, these are the possible values of capital X. None of them is less than this small x. None of them satisfies this. So we need to add anything over here. So capital Fx turns out to be 0 because we are adding nothing. So we are getting 0. So you see, this thing is satisfied. Now let's come to this case. Let me wipe out the board. Let's come to this case. Again, Fx is equal to summation over I such that xi is less than or equal to x, f of xi. So which all xi's will satisfy that? Xi values are 0, 1, 2, and 3. Only the xi value 0 will satisfy this. So this will be, in this case, f of 0. And how much is f of 0? That is equal to 1 upon 8. Say, for example, I'm just illustrating the same thing. Suppose x equal to 1.7. Just to take an example of this case. In general, for any x in this range, capital F of x will be equal to 1 by 8. We are just studying one example in that case, within that range. Suppose x equal to 1.7. xi values are 0, 1, 2, and 3. These are the xi values. That is the values possible for capital X. Now, among these values, only 0 is less than or equal to 1.7. So we will be adding up, this is summation of several things. We'll be adding up only F0 because 0 is the only number satisfying this thing. That's why we are getting F0, and that is nothing but 1/8. Similarly, if you take any number from 1 less than or equal to x less than 2, then you will have to add only F0 and F1, that is 1/8 plus 3/8 equal to 4/8. That's why you get 4/8. And for this range, you will have to add F0, F1, F2. So you get 1/8, 7/8. And when you come here, small x greater than or equal to 3, then in fact you add all the f values, f0 plus f1 plus f2 plus f3, and you get equal to 1/8 plus 3/8 plus 3/8 plus 1/8 equal to 1. This gives the distribution function graph of fx as we calculated in the last example. Fx for x less than 0, fx value is 0. So the graph comes like this along the x-axis, but not including point 0, up to before 0. This is important to note, up to before 0. As soon as it reaches 0, there is a sudden jump. And what is that jump? Starting from 0 up to before 1, fx is equal to 1/8. So this is 1/8. So starting from 0 up to before 1, this one, very important. It continues at the height 1/8. Then again, starting from the point 1, before 2, up in this range, it takes the value 4/8, as we have already calculated earlier. This is 4/8. And then 2 to 3, we know the value of fx is 7/8. That's why you get this range. This is 7/8. In this range, in this range. When x ranges over here, you get fx value equal to 7/8. And what is that range? Starting from the number 2 up to before 3, but not including 3. Next, when small x reaches the number 3, fx gets value 1, and it continues to be 1 forever, like this. For x greater than or equal to 3, fx value is 1. So the graph is like this. Now let's come to the continuous random variable case. Suppose x is a continuous random variable. We know for continuous random variable, we have got PDFs, and cumulative distribution function is anyway there for all types of random variables. Suppose capital X has got PDF small f and CDF capital F. In that case, they are related by this formula. Why is it so? Capital Fx for any number small x is equal to probability of capital X less than or equal to small x by definition. And that is same as probability of minus infinity less than capital X less than or equal to small x. And because small fx is the PDF of capital X, we can write this thing as integration of minus infinity to small x ft dt, because this probability must be the area under the graph of small f up to the point x starting from minus infinity. That's why this one. And see, that's what we have got here. So it follows from the definition of capital F and the definition of PDF of a random variable capital X. Now let us take an example of the continuous case. Suppose capital X is a continuous random variable and its PDF is given by this formula, this one. Small f of x is equal to 1 in the range from 0 to 1 and 0 otherwise. Then the CDF or cumulative distribution function of capital X is given by this formula we have already seen. So if we can compute this integration for different values of small x, then our job will be done. Excuse me. So let's compute capital F of x for different ranges of values of small x. See, what is the range of values for fx? Fx equal to 1 for 0 less than or equal to x less than or equal to 1, 0 otherwise. Right? In other words, the definition is splitting up the real number system into 3 parts. All the numbers less than 0, between 0 and 1, and above 1. This definition splits up into 3 parts. This component, and this one. Accordingly, let's find out capital F of x for all these 3 ranges. What happens for this range? If x is less than 0, in that case, we have fx is anyway given by this integration minus infinity to small x, this integration. And for any value of t less than 0, we have ft is equal to 0. That follows from the definition of small f, because small f one for this, 0 otherwise. And this part, all these t are falling in this otherwise part. So we get integration of 0, that gives you 0. What happens for this range? When x is between 0 and 1, in that case, fx can be split into these two integrations. What is fx? Fx is equal to minus infinity to x ft dt. And now x is between 0 and 1. So I can split this integration into two parts, minus infinity to 0 plus 0 to x. Minus infinity to 0, in this part, ft is 0. So this turns out to be 0. So only this part remains. And how much is that? Let me erase this part. This one turns out to be, I'm just writing this component. This is 0 to x. And in this part, it is ft is only 1. So this is integral is t 0 to x. That's why x minus 0, that is equal to x. So we get this one. So these two we have already got. How about this part? In this case, fx is nothing but an integral from minus infinity to small x, and that can be split into three integrations. Minus infinity to 0 ft dt plus 0 to 1 ft dt plus 1 to infinity ft dt. The first and third integrals are 0 because in these ranges, namely from minus infinity to 0 and 1 to infinity, in these two parts, ft, we know ft equal to 0. That's why the first and the third integral will vanish. And we will be left with only the second one. That means 0 to 1, ft is there, 1 dt, and that is t done. So we have checked all the three cases. And finally, combining these three things together, we get the final form of the function capital F. Capital F of x equal to 0 when small x is less than 0. Small x when it ranges, when it is in the range 0 to 1, excuse me, and for x greater than 1, it is equal to 1. If you draw the graph, it will come like this. It comes all the way here along the x-axis. Then, starting from 0, it takes the form, it goes along the straight line y equal to x. See, this goes along the straight line y equal to x. Because capital Fx value is same as small x in that case. And as soon as it reaches 1, then the value of Fx becomes 1 for x greater than or equal to 1. It remains 1 forever after that. let's talk about some basic properties of distribution functions. First property, fx is always between 0 and 1. Why is it so? Because by definition, fx equal to probability of capital X less than or equal to small x. And because it's a probability, we know that this number must be between 0 and 1. This number must be between 0 and 1 because that's the property of probability. And that property is translating into a property of cumulative distribution functions. Fx is monotonically non-decreasing. That means what? If you increase the argument, then the function value must not decrease. That's the meaning of non-decreasing. So this is the real number system. Here is x. You increase the value, that is from x you come to a value above x, that is y. At x the function value is fx. At y the function value is fy. Fy must not be less than fx. So fx must be less than or equal to fy. That's what this property is. What it says is, for x less than y, fx is less than or equal to fy. That always happens. Why is it so? Let's see the reason. What is fx? Fx equal to and what is fy? Now, two events we have. One event is x less than or equal to x, and another event is x less than or equal to y. This is one event, this is another event. Now, here is the real line. Here is x, here is y, because we are given x is less than y. Now, this event, when capital X is less than or equal to small x, means x is somewhere here. In that case, capital X must be less than or equal to small y. That means this is contained in this event. So they are related this way. So capital X less than or equal to small y is a bigger event, or at least as large as capital X less than or equal to small x. So this gives us, if the event is bigger, then the probability also must get bigger, or can remain same, but must not decrease at least, right? We know that thing. So that gives probability of x less than or equal to small x should be less than or equal to probability of x less than or equal to small y. And we know this is nothing but f of x, and this is nothing but f of y. So this is proved. Fx is right continuous. We won't try to prove that thing here, but remember this fact. Cumulative distribution functions are always right continuous. No matter whether the underlying random variable is discrete or continuous, cumulative distribution function is always right continuous. What is the meaning of right continuous and left continuous? Just a quick brush up. Suppose this is a point A. Now, suppose if the graph of f is like this. Now, suppose the fa, the value of the function fa, okay. Suppose f3 is equal to 0.5 and fx suppose I'm talking about general function, not necessarily cumulative distribution function. Suppose the function is like this: for x greater than or x greater than 3. In that case, what happens to the graph at the point 3? Now, in that case, at the point 3, the function value is 0.5. Now, for other values of x on the right hand side, it becomes, say here, as soon as you cross 3, it becomes 3.7 and more, right? So it goes like this. In this case, as your argument x approaches the point 3 from the right hand side, the right hand side limit of fx does not match with the function value at the point 3. So it's not a right continuous function. Whereas for right continuous function at 3, it will look like this, something like this. At the point 3, this is the value, and the function is continuous at this. So this function, capital Fx, is a right continuous function. However, we cannot tell whether it is left continuous or not. That will depend on the specific case, whether it is continuous random variable or discrete random variable, and what is the exact form, etc. But right continuous, it will always be. Remember that fact. Fb minus Fa is given by this thing. Why is it so? By the way, here I should have mentioned, for if there are two numbers A and B, A is less than B, in that case, this thing happens. I forgot to mention that. Please take a note. Here is A, here is B. Now, the event x less than or equal to B can be split into these two events, namely union capital X less than or equal to B is union of these two events, capital X less than or equal to A, and capital X is greater than A but less than or equal to B. Obvious, because whenever the right hand side is true, in that case, of course, capital X is less than or equal to B, and when capital X is less than or equal to B, then either it is less than or equal to B or it must satisfy this thing, no other. And observe that right hand side is union of two mutually exclusive events. So what can we say when we take probabilities? We can say that the probabilities should add up. So probability of this thing must be equal to probability of this plus probability of this thing. And now observe something. What is probability of capital X less than or equal to B? I'm writing here. That is nothing but f of B. And what is this thing? Capital X less than or equal to A. That is nothing but FA plus probability of A less than X less than or equal to B. And that gives property 4. If you take f of A on the left hand side, you get property 4. For any function, I'm talking about now 5. For any function, you can always talk about left-hand limit. That means here is the point A. You are approaching the point A from the left-hand side, and whatever that limit value is, that is denoted by f of A minus. Whereas when you approach the point A from the right-hand side, x comes from this side, then the limiting value is f of A plus. These are the notations, right-hand limit notation and left-hand limit notation. However, please keep in mind that not always left-hand limit and right-hand limit will exist for a function. For distribution, cumulative distribution functions, yes, left-hand limit and right-hand limits always exist. But for general functions, they might not exist. So here, this one, f of A minus means left-hand limit of A. Sorry, left-hand limit of capital F as x, let me repeat once again. Let me first remove this thing. F of A minus means left-hand limit of the function f at the point A. That's the meaning of this thing. When we take fa minus f of A minus, we must get probability of x exactly equal to small a. Now let's come to 6. If the function fx is continuous at A, then probability of capital X equal to A turns out to be 0. Why is it so? Let's apply property 5. When a function is continuous at the point A, that means both fa plus and fa minus both must be equal to fa. A function is continuous at the point A means both the right-hand limit and left-hand limit of the function will exist at the point A, and both of them, that is both the limits, must be equal to same as f of A. So in that case, if fx is continuous at the point A, fa minus f of A minus, that must be equal to 0 because of this thing. So this thing is 0, and this is 0 means what? Probability of x equal to A is 0 because of property 5. That's why we get property 6. Whenever fx is continuous at the point A, then this part becomes 0, and so probability of capital X equal to small a becomes 0. That's why this thing happens. As x goes to infinity, then capital Fx approaches to 1. That means no matter how the graph looks like in between, but as you take very large values of small x, then capital Fx becomes almost like 1. It may actually touch the line and continue, as we have seen in the discrete case, or it may so happen that it asymptotically goes towards this line. Either of these two cases. It may exactly become 1 and continue to be 1, or it may be like this asymptotic case. No matter what, this will limit of x tending to infinity fx equal to 1. As x tends to infinity, capital Fx tends to 1. And the other limit is as x tends to minus infinity, from fx equal to 0. What's the intuitive idea behind that? Let's understand that. See, here is the real line. Capital X will take values here. Now it has got a fixed pattern, right? Somewhere here with this much probability, that much probability, etc. Some pattern is there of values. And as you keep on repeating the experiment, you will be getting one value each for each trial of the random experiment. And the values will be like this. Now, if you take very high value of small x, very high value of small x, say for example, x equal to 10 to the power 19, very high value, then capital X will be almost always be less than or equal to small x. That's quite clear. Say, in that case, capital X will be almost sure to be less than or equal to 10 to the power 19. Right? So probability, when you calculate the probability of that, that will be like 1. Right? So that's why when you take very high value of capital X, then you are covering almost all the possible values of capital X. If you are not covered, those are really minority, and you can always include them by increasing the value of small x, because you are talking about these things, small x tending to infinity. That's why limiting value of probability of x less than or equal to small x as x tends to infinity, this is equal to 1. And capital probability of this thing, probability of capital X less than or equal to small x is nothing but f of x. That's why this thing happens. Similarly, when you let capital X, when you let small x become a very small number, something like small x is equal to minus 10 to the power 19, in that case, your capital X values almost always will lie on the right-hand side of small x. So in other words, this event becomes almost like null set. It will never be satisfied. So probability of this event will be equal to 0, or will be extremely small. So that's why limit of x tending to infinity, probability of x less than or equal to small x is equal to 0, and that's why limit of x tending to minus infinity, here it should be minus infinity. Minus infinity, that's why limit of x tending to minus infinity fx is equal to 0. So you get these two properties. When x is continuous random variable with PDF fx, we know in that case, they are related by this formula. We know that already. Now, in that case, if small fx can also be found this way, derivative of capital Fx. Actually, it follows from the second fundamental theorem of calculus, because that says, if capital F is given by this formula, then second fundamental theorem of calculus tells us that derivative of capital F will be same as fx wherever ft, if ft is continuous at x. So that's why we get this part. We have already seen how to get cumulative distribution function from a given probability mass function or a given probability density function. We have done that. How about the other way around? Suppose for a random variable, you are given the cumulative distribution function. Then your task, suppose, is to determine two things. Number one, whether it is discrete or continuous, or task number one is to determine whether it is discrete or continuous random variable. And task number two is, if it is discrete, compute its PMF. If it is continuous, compute its PDF. Let's see how we can handle this here. So here our cumulative distribution function is given, and we are trying to come up with either PMF or PDF. First thing to do is either plot the graph, or if you can imagine the graph, that's good enough. Plot the graph for the given distribution function. Now the graph will be either of the two types. It may look like steps with jumps at some points, as we have seen in the cumulative distribution function for the discrete case, or the graph might look continuous, as we have seen one example of. So either of the two cases. If the graph looks like steps, in that case, it's a discrete random variable. If it looks like a continuous thing, it's a continuous random variable. And then, if it is discrete, then we apply property 5 to get the probability mass function. What is the property 5? It tells you that probability of capital X equal to small a. Remember, when it is a discrete case, then we need to get the probability of X taking individual values. That is probability of capital X equal to small a for different small a values. So this thing we need to compute, and that is given by we will apply this thing. This is property 5. And when it is continuous case, we will apply property 8. That is fx equal to ddx of capital F of X. So first, identify what is the type using this. And then depending on that thing, either apply property 5 or property 8 of the distribution functions. Let's see here. It's a discrete case, we know, but nevertheless, we should be able to identify. Suppose fx is given by this form. Let's try to draw the function capital F, the graph of it. Here is -4. For x less than -4, the graph comes like this. It comes along the x-axis. At -4, it takes a jump. It becomes 2/7 as given by this thing, and goes up to, by the way, here when I am coming from here, the point -4 is not included, and to denote that thing, we are just drawing this way. Now, from -4 up to 1, here is 1, the graph goes along this thing, in this range. Starting from the point -4 up to before 1. So the graph is like this. Then starting from 1 up to 2.5, here is 2.5, the graph goes like what's the height here? This is 3/7 and so on. And for 2.5 to 4, 2.5 to 4, at the point 2.5, it takes another jump. It comes to the height 6/7 goes up to before 0.4, and at 0.4 it becomes 1 and continues like this. Here the height is 1. Now look at the form of the graph. Doesn't it look like steps? This is one step, this is another step, and so on. 1, 2, 3, 4, 5, 5 steps are there. So this is a discrete case. The underlying random variable must be a discrete random variable. Now, for the discrete random variable, what are the possible values here? The possible values are the jump points for the CDF capital A. What are the jump points for the jump points? Jump points of capital A. Which are those? The jump points are, first is -4, next is 1, first is -4, next is 1, then is 2.5, and then the last one is at 4. So only 4 jump points. And these are the places, the jump points are the places where capital X takes values. It can only take these 4 values, -4, 1, 2.5, and 4, nothing else. Now our task is to compute what are the possible values of these random variables. Or in other words, what is the PMF? Let's find out the corresponding PMF. So f of -4 that is same as f of -4. I'm applying property 5. F of -4 minus left hand limit at the point -4. This is a little confusing, but don't get confused. First -4, the -4 is the point. The left hand minus sign means -4 point. Now this one represents that we are taking the left hand side limit of -4. Now from the given graph, as you are approaching the point -4 from the left hand side, you should take this formula, right? Because you are approaching from the point -4 from the left hand side. So in order to calculate limit x tending to -4 capital F of x, all we need to know what are the capital Fx values for x less than -4. We don't need the value at the point -4. Please take a note of that. In order to calculate this, we don't need to know the exact value of f at the point -4. We only need to know what are the values on the left hand side of the point -4. And over there, the value is nothing but 0. So that's why we are getting 0. So yet f of -4 -0, and how much is f of -4? that is given by this range. F of minus 4 value will be given by this range. And in this range, f value is 2 by 7. That's why this is 2 by 7 minus 0, that is 2 by 7. So we have already got f of minus 4 is equal to 2 by 7. We have got f of minus 4 is 2 by 7. What are the other things? F of 1 should be minus f of 1 minus, sorry, f of 1 is given by this, and f of 1 minus is given by this range. In the, what is happening to the left hand side of 1, that is given by 2 by 7, that is limit of x going to 1 minus for 2 by 7, that is equal to 3 by 7 minus 2 by 7 is equal to 1 by 7. So what you can do is just see the jump amounts. Here the jump is this minus this, so 2 by 7. That's what we got here. And at the point 1, how much is the jump? This minus this, so we got 1 by 7. And how much it should be at the next point? Next point is 2.5. How much should be the jump? Jump should be this thing minus this thing. So it should be equal to 6 by 7 minus 3 by 7, that is equal to 3 by 7. And what should be f of 1? F of 1 must be equal to this jump. Sorry, this is not correct. Not f of 1, it should be f of 4. F of 4 is how much? The jump at the point 4. And that jump amount is this minus this. That is 1 minus 6 by 7. So that is equal to 1 by 7. So finally what we get is f of minus 4 equal to 2 by 7. Summation of those 4 numbers should be equal to 1. Let's see what is whether that's happening or not. 2 by 7 plus 1 by 7, 3 by 7 plus 3 by 7, 6 by 7 plus 1 by 7 equal to 1. So summation of the A values is giving you 1. That's a cross check. And this is indeed the case. The same thing is calculated here. The points of jump of fx are these 4 numbers. And we are applying this formula. F of 2.5 is given by 3 by 7. Similarly, this is equal to 1 by 7. We are just calculating the jump amounts here, as we described earlier. And finally, we get these answers. Now let us take an example of a continuous case. I shouldn't say continuous case at the very outset. We are taking another example like this, and let's identify the case, whether it is continuous or discrete. Capital Fx is given by this formula. 1 minus e to the power minus 3x for small x greater than or equal to 0, and 0 for x less than 0. So the graph looks like this. For x less than 0, it's coming like this. And for x greater than or equal to 0, by the way, for x equal to 0, how much is capital F0? That's given by this part. And that is equal to 1 minus e to the power minus 3 into 0. That is equal to 1 minus e to the power minus 0 equal to 0. Here onwards, it looks like this. See, this one, e to the power, it keeps on growing like this. It keeps on growing. Now, this one can never be equal to 1. Why is it so? Because for x greater than 0, this implies minus 3x is less than 0. This implies e to the power minus 3x is less than e to the power 0 because e to the power x is an increasing function, is a strictly increasing function. And e to the power 0 is equal to 1. So e to the power minus 3x is less than 1. So 1 minus e to the power minus 3x, that is no, that's less than 1, that's correct. But no. I want to show that this expression is less than 1. Look, e to the power minus 3x is positive, right? Because exponential e to the power raised to anything is positive always. We know that. So when we do 1 minus e to the power minus 3x, that must be less than 1. Isn't it? So for x greater than or equal to 0, what's happening? We are getting e to the power minus 3x is greater than 0. It always happens, not only for x greater than or equal to 0, it always happens. And that implies that 1 minus e to the power minus 3x less than 1. And when, in particular, when x is greater than or equal to 0, in that case, this is nothing but fx by this definition. So fx is less than 1. So we have got for x greater than or equal to 0, fx is less than 1. So this one, here is 1. The graph approaches asymptotically to 1. Why is it so? Is it actually going towards 1? As per the property of distribution function, it should. Let's check. Let me remove these parts. Limit of limit of x tending to infinity 1 minus e to the power minus 3x, which is same as 1 minus limit of x tending to infinity e to the power minus 3x. And that is 0. Because what's happening? As x goes to infinity, minus of 3x approaches to minus of infinity. So this one, as x becomes very large number, the exponent of this e becomes a very large negative number. And as a result, e to the power minus of 3x becomes extremely small. So as x goes to infinity, this number e to the power minus 3x approaches to 0 and we get 1. So see, here we have got a nice example. This capital Fx never touches the line 1, never touches this line. However, as x approaches to infinity, it asymptotically approaches to the line. Interesting case. Now, this one, as we drew the graph, we saw that fx graph or graph of fx is continuous. And because the graph is continuous, we can say the underlying random variable must also be continuous. So the underlying random variable capital X must be continuous. And when that thing is when the random variable is continuous, it must have a PDF, not PML. So in this scenario, we must calculate the PDF small fx of the random variable capital X. We know that small fx is related to capital F by this formula. If we take derivative of capital F, we'll get small f. And the functional form of capital F is given by this. Let me clear the board. Is given by this. It's given in two ranges. For x less than 0, capital Fx is 0. So in that case, we need to take derivative. If x less than 0, we need to take, in this range, derivative we need to take of 0. So we will get 0. That's why this part. And for x greater than or equal to 0, what happens? Here again, we need to take derivative of which part? We anyway need to take derivative of capital F, right? And when capital X, when x is greater than or equal to 0, then we are in this part. So we need to take derivative of 1 minus e to the power minus 3x, right? Let me write it down clearly. Fx is equal to, we are dealing with this case now, derivative of 1 minus e to the power minus 3x. And that is nothing but 3 into e to the power minus 3x. Combining these two cases, this case and this case, we get the final formula. Small f of x, that is the PDF of the random variable, will be given by 3 into e to the power minus 3x for x greater than or equal to 0 and 0 for x less than 0. That brings us to the end of this session, distribution function. So in the last 3 sessions, we have studied random variables, probability mass function, probability density function, probability cumulative distribution function, or in short, distribution function. And we have seen the links among these entities, how to find one from the other, how they are related. And these concepts are extremely important to deal with random variables and related topics. We'll see applications of these things in the future classes. Thanks for listening.